So why do we use I-beams as structural supports in our buildings? And how can hollow tubes make a strong chassis? The answer lies in the geometries of their cross-sectional areas, and specifically a property known as a second moment of area, or by another name, the area moment of inertia. Now, it might not be immediately obvious how an object's shape can affect its resistance to loading, and it can be even more challenging to build an intuition for the underlying mathematical description of the second moment of area. It's certainly a concept that confused me for some time in university, and if you're in a similar situation or you're simply trying to gain a better understanding of the engineering that surrounds us, I hope this video can help shed some light on the topic. So let's get into it. Let's imagine we fix our I-beam on one end and apply a load to the other. The I-beam will deflect under this load, leading to tensile forces stretching out its top surface and compressive forces compressing the bottom. The rotational force that drives this bending is called a moment, and it's a product of the applied force and the moment arm, or the distance from the applied force. As the moment arm increases, so too does the moment, which is why the tensile and compressive stresses increase towards the fixed end of our beam. If you need a refresher on stress, imagine we're applying a force to stretch a solid block. The stress is simply the force divided by the area on which it acts. A wider block will be stretched less under the same load, so by eliminating the cross-sectional area and considering stress instead of force, we can better generalize our analysis to a variety of scenarios. And much like the engineering students studying the subject, it's the stress that will ultimately cause the block to fail. Now, let's get back to the topic at hand and dissect the two names for this property for clues as to its significance. The term area moment of inertia essentially describes what this property does. Recall from physics that inertia is the tendency for objects to resist changes in motion. The moment implies that the type of motion we're resisting is rotation or bending. So, our area moment of inertia is essentially resisting the bending stress, with the area implying that it's the cross-sectional area of the beam that's responsible. The other name for this property, the second moment of area, is more closely related to its mathematical description. Recall that a moment arm is the distance from a force or object to its pivot point. In the cross-sectional plane of the I-beam, the moment arm is in the y direction. To get the second moment of area, we integrate the moments of infinitesimal bits of area. The second refers to the fact that we're squaring this moment arm. From this mathematical description, we can already begin to understand why certain shapes are just so strong. The contribution of one infinitesimal bit of area to the overall second moment of area is multiplied not only by its distance from the center plane, but by this distance squared. We could add a lot more material into the gaps of our I-beam, but the incremental increase in resistance to bending would be lower, and we'd be adding cost and weight to our design. Of course, this conclusion depends on the assertion that the area moment of inertia does indeed increase an object's resistance to bending. But how does it do so, and why does it take on this mathematical form? To answer this, we'll need to zoom in on the most fundamental building block of our material's strength, the atom. For small movements, the bond between atoms can be represented by a linear spring. Now, let's attach a rod of length y to one of the atoms and apply a moment, just like the one seen by our I-beam. The spring will stretch some distance ds until its restoring force is sufficient to counteract the applied moment, resulting in a displacement angle d theta. Since this is a very small angle, we can approximate and write ds equals y d theta. We also know that this system is in equilibrium, which means that the restoring force F times the moment arm y must equal the applied moment. And finally, we can add one more equation to our model, that of the linear spring, which states that the restoring force is equal to the displacement ds times a spring constant k. Now, let's rearrange our equations to get the angle d theta in terms of our applied moment mz. We'll place d theta on the left-hand side of the first equation and rearrange the linear spring equation with ds on the left-hand side, which allows us to substitute it into the first equation. Already, we can see one way in which the distance from the pivot point reduces the displacement angle. Since the linear displacement ds is proportional to the distance from the pivot, and the restoring force of a spring is proportional to the distance it's stretched, the displacement angle is reduced by one factor of the distance to the pivot. In other words, for a given angle of displacement, atomic bonds further from the center of rotation will be stretched more, resulting in a larger restoring force. But we aren't actually interested in the restoring force of a single atomic bond. We want to know the effect of the applied moment itself. To do this, we'll rearrange the moment arm equation for F and substitute it in. In doing so, we introduce a second moment arising from simple mechanical advantage. The further the pair of atoms is from the pivot, the smaller the restoring force of the spring has to be in order to counteract the applied moment. We've now uncovered the origin of the two moments in our second moment of area. But where's the area? Well, In a real object, it would be silly to sum up the individual contribution of innumerable atomic bonds. Instead, we can zoom out a bit and consider an infinitesimal area of bonds dA. So how does this area fit into our equation? The physical property that represents the strength of the atomic bonds is the spring constant K. Let's replace it with our infinitesimal area times a quantity E prime, which is the spring constant per unit area. This helps to generalize our equation, but we can go one step further. If we think about a spring, its stiffness is governed not only by the geometry of individual coils, but by the overall length of the spring itself. A longer spring will stretch further under a given load, reducing its stiffness. We can apply the same logic to our infinitesimal bit of area if we extend our model into the third dimension and consider an infinitesimal thickness, dx. The spring constant is now divided by dx, and E prime becomes E, a material constant known as the Young's modulus, or the modulus of elasticity. Plugging everything back into our equation, we have a general formula to describe the displacement angle of an infinitesimal slice of any given material under an applied moment. Already, we can recognize the mathematical form of the second moment of area. The question now is, how does this generalize to the entire cross-sectional area? As it turns out, when we add a second infinitesimal slice to our model, the second moments of area add together. This is because the atomic bonds in our cross-section are constrained to share the same displacement angle. The same is true for adding a third area, and so on. And what is the summation of infinitesimal quantities if not an integral? We have finally arrived at the formula for the second moment of area, which we can now place into our equation, showing that it does indeed reduce the bending under an applied moment. This equation is quite versatile. Under the point loading condition described at the beginning, we can integrate this equation along our I-beam to arrive at the overall angle of deflection. We can also find the magnitude of normal stress induced by a moment in a beam, or the deflection in the y direction caused by this bending. In all of these, the second moment of area plays a key role. I'll leave these derivations as an exercise to the viewer. Lastly, an important thing to note is that all the math we've done so far assumes a moment in a particular direction. When we can reliably predict the direction of applied forces, such as with beams in our buildings, we can optimize our supports to get as much cross-sectional area away from the neutral plane as possible. That's how we get the I-beam, and it is very strong at resisting vertical forces. But any object does not have one unique second moment of area. If we turn the I-beam on its side, its second moment of area changes, and its ability to withstand vertical forces is reduced. And I guess that's why we don't see a lot of H-beams holding up our skyscrapers. Thanks for watching.